So now we are officially on air, and I'm going to take another screenshot, but I want to get to the point where, okay, Brandon had something up there for a second.
Oh, it's just OBS. I'm trying to figure something out.
Okay, anything that if it helps me if it has a little bit about your, I mean, Gibbon. If I see SpaceX, I know it's Gibbon. So you can always just do a picture. It depends on how much privacy you want. Okay. So we only have till two o'clock. I'm going to feel a little rushed. We got into a wide range in discussion. And the thing about this is this has to be the wrap up. This is the official record of what happened in class. I mean, I can screw around in class all I want, but I cannot really, I've got to have this, this goes down in the record books. So I can't screw around that much on these things. Yeah. Oh, man, we got to a lot of wide-ranging discussions. Fridays get that way, I guess. All right, so let me get this set up, and then I'll share the screen. So we started off today going around giving out doggies. And so for them, we made this, finally came up to this conclusion that we're going to go with, I say we, I mean the class had a say in it, I guess. But I'm going to do 25 doggies for Pkt4, 25 stamps. And each stamp is 2 points each. So that means 50 points. That means so what I'll do is I'll prorate that to your papers you're going to turn in. So those that missed it, Io, Anthony, some of you didn't, Miranda, some of you didn't hear this, to balance out the stamps that they're having to get and to keep you guys honest and keep you guys up to date, I'm going to require one sheet a week. Now we're going to go over more than one sheet. Like right now, we're also on 4.2, but we spent most of the week on 4.1. So 4.1 will have to be completed by you and submitted, not emailed. I'm going to make it an assignment only for virtual students on the Canvas. So you'll see the assignment. Normally I think these are, because I can't post a key. A lot of kids are wanting to see the key. They've tried it and they're not sure if they're right. So now they want to check the key. I've gone around, I give them credit for trying. So for you all, normally I think it's reasonable to say that Friday, normally I'll say Friday at midnight, so it'll only be tonight at midnight, you would have to submit, like in this case, sheet 4.1. But because this is new notice to you, I'm going to make it Sunday at midnight for you all. Now I can't post a key until you submit it. And then you'll be penalized for being late if you're after that. But then, you could always, I want you to look at the key. You're going to look at the key. But I'd rather look at the key after you submitted with your best guess. And then I'll give you points. Whatever many doggies know. Okay, however many total points occurred that week in stamps. Like this week, we've had something like 20 points worth of stamps already. Then that paper will be worth 20 points. Okay, so it'll vary depending on whichever paper we pick and how many stamps are on that paper. This is complicated, but that's the way to keep it fair. That's what I'm coming up with as of now. All right. So the bottom line is you're going to get an assignment. You'll see it today, this afternoon. It'll be for you only, virtual only, and it'll be to turn in 4.1, submit it. Don't do it yet because there's no assignment yet, but this afternoon there will be. Submit 4.1 by Sunday at midnight. Normally it'll be Friday at midnight, but this time Sunday at midnight for up to whatever many points it was. That's a little bit closer to fair. Okay, it is, let's go ahead and share the screen. Sharing, yeah, sharing. All right, cable, share it. Okay. So today was Flashback Friday. I wish we had time in here, but we are at 50 minutes and we've cut it to the bone now. And because it's a wrap up, we screw around. The last 6 minutes of class on Friday is Flashback, where I play music and they have to guess the artist, anywhere from 1940 up to 2020. So there was the dogs that we did. And this is what I was telling these guys, if you didn't hear this, 25 dogs or 25 stamps, or that equates to 50 points. 50 points will be on Pkt4 will come from stamps. And these are the problems that they've had to do. But I only want to take one sheet at a time. I don't want you submitting 2 sheets. So the sheet you're going to submit is 4.1, but you have to have the whole thing done. I mean, you know, some stuff we'll do together, but then you have to have the whole thing done. Because they also did some other stuff on 4.1. Yesterday, a couple days ago, we did 4, where we talked about throwing something up and catching it. And then we did this one, number 3. We finished number 3. And number 3 turned into, hold on, number 3 somewhere here, we turned into green. There it is. So this was us yesterday. Oh no, this was number 3. This was for this one. This was number 7. And from there, we actually developed a green equation, which we officially developed the green equations on Monday. So we're a little ahead there. That's good. The other classes haven't done it. What else did we do? The main and most important thing about yesterday was we talked about this. Let me explain this to you. So we did this. We already explained it to you, but let me go over again. This is a trio, a negative trio. Throw a ball up, catch it. The Y, the VY, and the AY. All right. This is the standard. Now, on the test, you'll have something like this. You'll have a question that looks like this, and it'll give you, like, it won't be all 7 of them, but it'll be like 3 of the 7 situations. And it'll have the graphs. It'll say, okay, now sketch for me. I sketch what happens if I throw a ball down and it lands below me. And now you got to sketch what that looks like. Well, that is this sketch. Okay. Well, I'm allowing this. A couple of years ago, a student did this on a test, and I thought, okay, I'll allow that. And what they did was, I thought it was pretty smart. They drew this on every one of those, all 3 of them. They drew this trio, and then they erased what they needed to erase. And I thought, you know, technically there's some glitches there, but it's pretty good because I think you'll remember it better that way. So, like, for instance, if I said you throw a ball down on this one, you would draw that, and then you would erase all of that. You'd erase everything in yellow there, and all you have is that. And I know the timing looks a little weird, but I'll accept that as a correct answer. Okay. Or if I say you throw a ball up and it's caught after it reaches the apex, then you erase that much of it. See what I'm saying? We're going to start doing practice problems next week. And that'll be something that'll be a big Facebook thing. Hopefully you're on there, because it'll be a lot of Facebook back and forth on, because we're not going to talk about backup problems in class. That's a home thing to do. Of course, everything for you is a home thing, but that'll be just a homework thing. And you can choose not to do it, but then your test is going to be a nightmare. Okay. That's the way college is anyway. So there's the 7 situations. This is on the Facebook. If you want to split screen, open Facebook up. This is on Facebook from yesterday. And then here, this is also on Facebook. And this is just more detailed example from my book there of using one of the situations where it's still using, you know, you can use equations, you can use, this is using the graph. Okay. There's that. Okay. So this is the homework. If you want to keep up with the class, with what's going on in class, you may end up turning in 4.2 next week. Probably that'd be the one. It'd be 4.2 or 4.3. but probably this 4.2 would not be due for you until Friday, the 15th of January. That's my guess right now. But these are the dogs. They could have gotten 3. A lot of them did. They're doing a really good job here of keeping up, most of them. You got 3 dogs for those, doing a real good job on those 2. So far, 4, 5, 6, 7 dogs already on 4.2. Now we're going to do the back together. So that's the most you'd have, would be 7 dogs on that one, or 14 points. So this is not really in-class stuff. To keep up, you were supposed to have done number 1 and 2. Those are fairly straightforward. 3, 4, and 5 are this weekend. And all they had to do was give me a good solid effort. They didn't have to be right, but the answers are on the back. Okay, so what we worked on was in class, we started talking about this yesterday, and now this is going to get me into a whole nother ball game. And this will take, today we'll take some notes. I'm going to apologize in advance. You'll be taking some notes or just listening. But this will help your notes, because the notes for Pkt4 is like 100 points. I mean, it's a lot of points, or at least 75. All right. So we started talking about this yesterday, and the idea of this is a nut coming off an elevator, the bottom of an elevator, and you see this all the time in every physics book. Textbook has this question in various forms. A lot of times it's an elevator. So the nut comes off a screw on the bottom, and then it falls to the bottom of the shaft, the elevator shaft. And the question is, if the elevator was rising at 4 meters a second, the nut then strikes the bottom in 2 seconds. How far did it fall? How far, or what floor? Sometimes they ask, what floor is the elevator on? And it's about 3 meters of floor, somewhere in there, 3 to 4 meters of floor. So the path of that, because of momentum, the path of that little nut, it continues to rise because of momentum, and then eventually gravity wins and it turns around and comes back down. Okay, so let's do A. Let's go ahead and get the A and B. I'm going to run out of space. I'll put A down here and then B as well. So A says, how far from the bottom of the shaft was the elevator when the nut fell off? Now I'll shut up, and it doesn't do any good to pause because I can't. We're going to have to go ahead and just keep it going. Actually, I think I will pause, so somebody watching this doesn't sit and watch dead airspace. I just worry that I forget to start it up again. All right, we're back on the air. So now the first time you write the equation, give me this. This is your standard practices in physics. Pretty much any physics professor worth his or her salt will make you do this. You got to write the symbol equation, then you got to write an equation with all the numbers and units in it, and then you go right to the answer. But we got to see at least that much. Just giving the answers doesn't do any good in here, because guess what? All the answers are already at the bottom. So students that just give me answers, they don't get any credit. I can copy down stuff. And that would be 4. Okay. So your delta Y, when you punch in your numbers, it's 13 point, let me cheat, 13.6. So delta Y is 13.6 meters above the bottom of the shaft. All right, that's not that interesting. But then we go to part B. And part B says, how far above the bottom was the nut a quarter second after it fell off? Okay, so do it again. This time, put in a quarter second. So you do it and I'll do it in silence. Over here. Uh, okay, I just said you had to do this, so I guess I have to do it. I'm the worst about telling you to do stuff, and then make sure that point two, one of the main mistakes students make on this is they forget to square the time on the end. I had Finn swearing to me that I was wrong. And he said, I've done it 2 or 3 times. Yeah, well, then oh, shoot, I didn't square that time. Now, when you go ahead and do the math here, you get that this is what, 0.4? Something like 0.44 or something? Positive. And I remember when I was a student teacher, we were doing this problem in class back in 1985, 86. And that bothered me. What? That can't be. You drop a ball. I mean, I wasn't thinking, right? When I first did it, though, I thought, oh, I must have made a mistake. If you look at the bottom of that, you look at the bottom and it says the answer is 14.1. And I thought, no, I'm keep getting 0.44. Why is someone explain that to me? Why, if the answer, if I'm getting 0.44, why is the answer 14.1?
Because it's above the bottom of the shaft.
Right, above the bottom. So we were already at 13.6. Yeah, so 13.6 plus 0.44 puts us at about 14.1 meters above the bottom of the shaft. Okay, that's fine. I get it. But that's weird. It was weird when I first did this problem and hadn't thought about it very much, because that says that I drop say I drop this speaker here. I drop this speaker, and a quarter second after I drop it, it's above me. And I didn't have to bring it up. A couple of students brought it up. So how is that possible? And what say you? Now remember, I can't require it yet, but I'm going to find a way to make each of you participate at least once, preferably twice, during these sessions. So you have to mic up and somehow.
Is it because of momentum or moving inertia that we talked about yesterday?
Yes, exactly right. So, and I'm starting to get to know your voice. I know Sophia's voice, but I'm just trying to think how to monetize that, or how to not monetize, how to quantify that. Okay, every time, to give you some incentive to mic up and to say something. Even if you're wrong, every time you participate, you mic up and say something, you hit the mic and say something. You get a Zoom point, and I can't keep track of this, so you got to keep track of your own. It's honor system. And let's say you can get a maximum of 3. A maximum of 3 Zoom points. Those will add up. That's 15 points a week, up to. Okay, so new rule. All right, so Sophia said because it has momentum, and so my speaker, I wasn't just dropping my speaker, I was throwing my speaker up. And when you throw it up, a quarter second after you throw it, it's still rising. Maybe it's coming back down, but it's above where you let it go. And that's the idea of momentum, which is like moving inertia. Okay, so this led to a whole thing. So here we go with some notes. Now you need to get your notes out. All right, let's go back to, let's go back to inertia. Now, inertia is no little deal. We recently spent $15 billion. $15 billion, the world did, trying to understand inertia, trying to understand mass. Inertia itself is fairly simple, I guess. I had a student named Max Rhodes. I don't know if you guys know the Rhodes. Max Rhodes, a few years ago. And Max was, all the girls swooned over Max Rhodes. Tall, blonde, blue-eyed, soccer player, soccer star, Aegis, everything, went to Yale. Just this guy. But Max's weakness was physics. He struggled in my class. And he worked hard because he's, a hard worker and all. But he was more of a linguist, right? He's more of a English kind of person. But he finally said, I just don't get this inertia. He said, Mr. Ostrowski, can I, after we talked about it a while, I said, can I just call that, for myself, can I just call that resistance? And I said, you bet. It is basically resistance. That's all it is. Anything that resists something has inertia. Now, in our universe, anything with mass resists changes. It resists okay. So basically, another way to say it is inertia is resistance to change. Okay. Now, some marriages stay together because of inertia. I mean, it's easier to just stay married to that sad sack, whoever you're with. I mean, say I'm lucky myself, but let's say that you just don't get along with your spouse, but it's easier to stay married to them than it is to get a divorce, because you get a divorce, you got to, divide the furniture and who gets the dog and who gets the kids on weekends and lawyers. And so a lot of marriages, you'll find this out someday, is still together because of inertia. And then there's the lucky few, like Jamie and I. But that's so that is it in another. Okay, another example. This morning your alarm clock went off and you didn't want to get out of bed. That's inertia. That's resistance to change. Okay. So the first person, I asked the kids in class, who was the first person to think of this? Newton, Einstein, no. It was before Newton. And then someone said, well, it's Da Vinci. I said, no, wasn't Da Vinci. It was after Da Vinci. Da Vinci thought about falling, but he didn't really have a concept of inertia. It was actually Galileo. So Galileo was the first, and then right after him, Rene Descartes. Kepler somewhat, but mostly Galileo, and then Rene Descartes, and then later Newton came along and got all the credit for it. So let's write out Newton's first law. You've heard this one before, but we need to write it out. I used to make kids memorize this. Newton's first law. It's called the law of inertia. We are recording this, yes. How much time do I got? 25 minutes. I gotta go. All right, here it is. It says, let's say it the way we said it in class. What did we say? We said a body. Okay. So it could say an object or a body. I think in class with a body. A body at rest remains, let's say, Newton said it in very flowery. So we're not going to do as flowery as Newton did it. Remains at rest, right? You've heard this before. And what's the next part? A body, keep going. I say it again. Say it to me.
A body in motion stays in motion.
Okay, a body in motion stays in motion. Let's complete that though. Stays in motion.
Unless acted upon by an outside force.
We're almost there. We're not there yet. Stays in motion, but wait a minute. You got to say a caveat. Stays in motion at the same velocity. That's crucial. At the same velocity. Now, remember, velocity is a vector. So velocity can be the size, how fast you're going. It's also the direction you're going. So if you're in a car and you are turning a curve and you're turning that curve at 30 miles an hour, that you are having to change your inertia because you're having to change your direction, right? So at the same velocity, and then the big unless the big unless here, unless, and now it's acted upon by what? Say it again.
By an outside force.
Almost. I'm going to give you a zoom point for that, but by an, it's not just an outside force.
An unbalanced force.
There you go. Okay, so now you two tag teamed on that one. Very good. So point there to you too. I think that's Io. Unless acted upon by an unbalanced outside, or the more fancy word there, outside's the $5 word. The $10 word is external. So let's say external. Unbalanced external force. As opposed to an internal force. Internal forces are forces inside a system. And you when you're first working a physics problem, as we're getting ready to get into, more into Pkt4, but we'll remember at the very end of Pkt3, we did that car going up a hill, we drew all the forces on it. That's really Pkt4. But all those forces acting on a car going up a hill, we only draw the external forces. All the internal forces are within the engine. The little kid in the back seat, playing with his Nintendo. Those are all internal forces, and those cancel. As Newton figured out, all internal forces cancel. Like I can't pull myself to the ceiling by pulling on my hair because my body that's internal force. Okay, so that canceled, right? So it has to be external force, all acted upon by an unbalanced. So if it's balanced, it's called equilibrium. Things are in equilibrium. If I'm going down the road on cruise control, that all the forces on me are balanced. All right, so I'm not accelerating. So a body at rest remains at rest, and a body in motion stays in motion at the same velocity, unless, and I think Newton added in a right line. But in a right line means in the 1600s meant going straight. You're going in a right line. You're going straight. But you don't need to say that because velocity is a vector, which takes into account, and vectors are just starting to come in vogue with Newton. But you don't need to, because velocity tells you that the direction's the same, and it tells you that the magnitude's the same if it's the same velocity. Okay, at the same velocity, that's acted upon by it. So that is putting into words what Galileo had kind of said, and then Descartes had said, but Descartes was a philosopher. Descartes has been called the French Newton. But Descartes, I got to be careful. I'm running out of time. One quick story on Descartes. Descartes got in trouble because of something called vis viva. He said that moving objects had a life force in them, vis viva. And so more of a philosophy thing, but that also got Gottfried Leibniz in trouble. And Leibniz was one of the inventors of calculus because Leibniz agreed with Descartes and said that things that move have a life force. And people were calling them occult, and they were misinterpreting it, but you're ascribing to the occult. And so they lost favor, whereas Newton didn't say that. Newton kept them as inanimate objects. He kind of Newton did not understand inertia. But let's give the guy a break. I mean, we spent $15 billion and we still don't understand inertia. And by the way, that was at the Large Hadron Collider. We're still working on it. A guy named Peter Higgs in the 1960s is still trying to understand what is this resistance to movement? Why do objects with mass resist motion or resist a change in motion? And guess what? Nobody knows. Nobody knows. Photons, which is light, has no resistance. Light does not have mass, it has no resistance to motion, to change in motion. Things that have mass, that have a resistance, cannot go at the speed of light. They have a limit. Their mass becomes infinite if they try to go at the speed of light. We didn't figure that out till Einstein, right? So that's within the last 100 years, give or take. So this stuff, this is still modern day. This is not just some ancient physics we're talking about. I mostly teach classical physics, but this is modern day, still modern, has implications, and Large Hadron Collider stuff. Okay, good. And now the last thing I want to talk about, maybe a little more than this, but not much more. I was shocked during second hour when I didn't come up first hour. But if I throw this pin up in the air, eventually, it goes off screen, but eventually gravity does take hold of it and bring it back, right? But gravity is weak. I mean, it's kind of like the Capitol Police, to be topical here. It's weak, man. It lets it through. It lets that pin, it like stands back and lets the pin rise. Even though I'm not lifting it up, it still rises because of inertia, right? But that is so weak that and this came up from Ryland in first hour, said, but why does that nut, why does it just fall down? Why does it keep going up? I mean, such a brilliant question. That was second hour. It's a brilliant question. You have to walk into physics innocent and ask the innocent questions. You have to say, the emperor wears no clothes, and look that one up. But it's like, as a child, you need to see the universe as a child. And ask those questions. Why is the sky blue or whatever? I mean, why? Ask those questions that you had when you were 7. And the cool thing is that now we get to answer them because we have a little math under our belt. Okay. So that brought up in second hour, this idea of gravity being so weak. And I said to my second hour, I said, you all know that gravity is so weak. And they all look at me like, what? What are you talking about? I said, it's the weakest of the 4 fundamental forces. And they stared at me like, what are you talking about? I said, oh, no. Okay. So now we're going to have to talk about the 4 fundamental forces. This is supposed to be done in chemistry. Doggone it. We always taught this in chemistry, but I guess it's not being taught now, or they dropped it for some reason. But I guess it's up to me now. This is, by the way, I'm not going off on a tangent. This is standards. This is in the physics standards. 4 fundamental forces of the universe. So this is big time now. 4 fundamental forces in the universe. I mean everything. Our galaxy, Andromeda, Triangulum. 4 fundamental forces in the universe.
Are some of them nuclear forces?
Yes. Aha. Miranda, now daggone it. I know you know this because they had to have gone over this. Pal had to have gone over this in AP chemistry. So Miranda, I'm going to give you that one. But don't give me all 4 of them. Let's let everybody else try and think through that one. Hold on. Second, third, let's put them in order. 4th. So wait a minute, Miranda. When you say nuclear forces, let me come back to you for a second. What? Yeah, go. Give me a little more of that. What do you mean?
So like the interactions between the bonds, like London dispersion, maybe?
Oh no, that's London dispersion forces are interactions between molecules. If you're saying nuclear, you're saying subnuclear, right?
Or the intramolecular instead of...
They are, nope. Intra is the bonds within a molecule or within a compound. Those are intra. Inter, like like a hydrogen bonding is intermolecular bonds. The bond between the oxygen and the hydrogen are intramolecular, they're within the molecule. But I'm going even deeper than that. I'm going into, not only into the atom, but into the nucleus. Okay, let's come back to that.
Nuclear.
I'm giving you the credit on that. It is nuclear bonding. And so what we call it is, what I was trying to get you to say was, this is, by the way, the strongest force in the universe. It's SNF. Now, Miranda, what's the S stand for?
Strong nuclear.
Thank you. Thank you. So strong nuclear force. And let's make a little table up here. This is the table that you should know when you graduate high school. Okay, that'll be the name, and this here will be the strength. And this will be the range. The range. So strong nuclear is the strongest force that we know of. Now, this doesn't take into account dark matter or dark energy. We don't know. We do not understand those. We don't have a set of equations for those. The strength of the strong nuclear force is 10 to the 37th. Now, it's relative. The range, okay. Let's hold up on the range. Okay, so Miranda answered one. Somebody else give me another force.
Would electromagnetic force
That
be
is,
yeah.
ding, 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 ding. That is number 2, electromagnetic. Electromagnetic forces, and they are 100 times weaker than strong nuclear. They are 10 to the 35th. Now, they used to think back in the 1800s, I'm talking about Michael Faraday and all those, thought that electricity was one force and magnetism was a whole different force. But it was Faraday himself and Oersted and Ampers and Volta and all these people who you name electricity stuff after now, and Maxwell, of course, that showed that electromagnetism was really one force, They go together. You can't have one without the other. But that's the second strongest force in the universe. Now, you learned about, of course, electromagnetics in chemistry. Because in chemistry, you learn that what happens if I bring two positives together? What happens? Bring a plus and a plus together, what happens?
They repel.
They repel. So they're going to shoot out. If you put it onto if you do those metal shavings, which I hope they still do in chemistry, but you put out two positive or even magnets, all the shavings come out like this, and they basically shoot out they're photons essentially that repel each other. So like charges repel, right? Well, didn't that bother you? Like if you look at the periodic table, you got hydrogen, okay, you got helium, then you got lithium, the first solid. Lithium, in the nucleus of lithium, you have a proton, you have a proton, you have a proton, you have a neutron, let's say it's three and three. So, but how the heck, if those are positively charged, they should not come together, right? They should not, they should repel each other. A lithium atom or beryllium or boron or carbon, you want to go to nitrogen, go on down the list, those should self-destruct, because the neutrons aren't going to do anything. They're neutral electromagnetically. They have no charge. But those two protons, that's the second strongest force in the universe. There's no way they should be held together. Well, what holds them together is the strong nuclear force. Now, the force carrier for that, by the way, this all came from a nut falling off an elevator. But the force carrier for that's what happens in physics. You get to talk about something and you can talk for days and just go in and in and in and in and in. That's what Richard Feynman does. If you go look up Richard Feynman on YouTube And he's sitting in a blue chair. It's the 1960s, and he's a cool dude. Richard Feynman's one of the coolest people, not just physicists ever lived, one of the coolest people ever lived. Caltech guy. But he sits in his chair, and they ask him a question, and he goes on for hours. It's amazing. This guy's amazing, and he's interesting. Anyway, look up Richard Feynman. So the force carriers for these are something called gluons. Gluons. Okay. They essentially glue the nucleus together. Okay. They're little interactions between the protons and neutrons of the nucleus. Now, the gluons, the force carrier is gluons, and that usually goes in our table, but we're not going that far. That's the source of strong nuclear force. Photons are the source of electromagnetics. Those are photons, but gluons beat photons. Okay, give me another force. We only got, we're down to 7 minutes. Give me another force. There's 4 forces in the universe.
So if there's a strong nuclear force, would there be like a weak nuclear force too?
Weak. Okay, that's number 3. Weak nuclear force. So a point there. That is also strong. It's weak compared to strong, but it is 10 to the 32nd time. So it's 1,000 times weaker than the force that basically the force that runs our life. Yes, if we didn't have strong nuclear force, we'd all self-explode. But the force that runs our life is electromagnetics. We all chemical reactions are basically electromagnetics. Weak nuclear force is what makes the sun shine. So it's not that it's trivial. It just doesn't play a big role, except it causes the sun to shine, which causes all life on Earth. But yeah, on a daily basis, like when I do this, like if I look, my hands never touched, right? My hands never really touched. What came in contact was electron clouds, right? The electron cloud of this palm and this palm. But my hands never touched because I can't get through the electron clouds. They're so much stronger than anything I can do. That's 10 to the 35th. So yeah, this, and then finally, what's the weakest of the 4 forces?
Gravity.
Gravity. Thank you. There's a point there. Gravity is, if all of those others, gravity gets a 1. So strong nuclear or just electromagnetics is a 1 with 35. I don't even know what that number's called. It's way past a tera, Tera is 10 to the 12th. We're at peta is 10 to the 15th. We're at 10 to the 35th. I don't know if there's an atto or something. I don't know what the name of that is. But that's how much stronger electromagnetics is, which, by the way, works together with gravity all the time. Here's the problem with strong nuclear and weak nuclear. It's like Aladdin. I don't know if you remember. There's a movie called Aladdin. It's a cartoon. And the genie comes out of the bottle. And the genie says, "Oh, been cramped up." And they talked to him and said, "Yeah, man, you're all powerful." He said, "Yeah. All the power in the universe, itty bitty living space." So he has to live inside that lamp, right? And that's exactly how you describe strong nuclear force. All the gluons have all the energy, all this force of the universe, but it's contained inside a nucleus. And so now we're talking about, when I talk about a lithium atom, I'm talking about when I go across, look at the diameter of a lithium atom, I am on the order of femtometers. So we're talking about the range here is 10 to the negative 15th meters. That's 1,000 smaller than a picometer. So yes, you do have a lot of power, but you don't have much range. Weak nuclear is even worse. Weak nuclear is 10 to the negative 17th meters. 100 times smaller range than a strong nuclear force. What about electromagnetic? How far do you think a positive and a negative would attract each other? How far can you go? Like if I had one proton and another proton, and one proton was in Oklahoma and another proton was in Dallas, one's in Norman, one's in Dallas, would they still repel each other? What do you think?
Maybe like very, very weak.
Very, very, very weakly, but they would repel each other. And so electromagnetism is infinite in range. And then when you get to gravity, isn't Pluto, or let's go, since Pluto is not considered a planet or a dwarf planet, let's say Neptune. Isn't Neptune held in its orbit by the sun? Yes. So gravity is also, I mean, we're being attracted to Andromeda. I gotta be careful there. There's some dark matter involved there, but there is system gravity. Anytime massive objects for some, there's another weird thing about it, about inertia. Inertia attracts inertia. Isn't that weird? Resistance attracts resistance. So, because massive objects attract each other, the moon is attracted to the Earth. So that's also infinite. That's the advantage. Gravity is the weak link. In fact, it's so weak, Einstein said it doesn't even have force. And the final thing I wanted, so since we talked about gravity being so weak, that's important. This is important, especially when you go on into physics, into modern physics and stuff, and electromagnetism. What runs the show here, we did blue equations, right? Blue equations kind of help us understand gravity, at least the kinematics of it. But what helps you understand electromagnetics is something called and look these up, you are just for fun, Maxwell's equations. Look up Maxwell's equations. You won't get into Maxwell's equations until towards the end of electromagnetics. We do it at Norman High School, but it's a third year of physics, which we didn't do this year. But normally we would do a third year of physics, and in there we do talk about Maxwell's equation. Okay, last thing, I forgot, let's wrap this up. Back on Newton's law, if we want to put this on a t-shirt, that's not going to look good on a t-shirt. It's going to go on the front, the back. If I want to boil this down to 3 words, I want to turn this into 3 words. So last thing here, Newton's laws, Newton's first, in 3 words for the t-shirt. And we don't have time, we only got a minute. So it's this. What is it? I'm going to say mass. So mass, here we go. Mass resists, a change in velocity, which is called acceleration. So mass resists acceleration. There's your meme. There's your t-shirt idea for explaining Newton's first law. Mass resists acceleration. If you know that, you know Newton's first law. And you can get through a lot of physics just knowing that. Okay. We got through that. So now you see your homework, being virtual, is to submit, and this afternoon I will put this on the canvas, is to submit 4.1 for your points. Okay. The in-class kids did it through little doggies, and you're going to do it through a submission. Let me turn this off. Okay, everybody. Oh, I'm going to take a screenshot. Since some of you don't have your icons up there, that's another homework, is to work on icons. Gibbon has one, Bennett does, Ellie does, Eric does, but give me a good icon that I can remember you by. And then if I forget to just do what I just did, it'll be on the YouTube. I can quickly look at that and know who was here. Okay, I'll put this up on YouTube sometime this afternoon. All right, you guys have been a wonderful audience for a Friday. Thank you all. Like, thank LA for coming in, and I think Brandon's here still. And I know some of you can only be here some of the time because of other classes, but I appreciate it. And Andrew as well. I appreciate you guys joining us at least a couple of times a week, I hope. All right. Anything before we go? Any questions?
I have a question.
Yeah.
So when you say turn in 4.1, do you mean like everything on it or the first page?
Yeah. First and back, front and back. And you'll get whatever the doggies were for that. However many doggies I gave out this week, that'll be the points. And I think it's like 15 or something, whatever it is. So those points will vary depending on doggies, depending on stamps. Okay, that just keeps you even with the in-class kids.
And you said that was due Sunday, right?
Sunday at midnight.
All right.
Normally it'll be due tonight at midnight, Friday night at midnight. Okay. Look, we're going to, I think maybe we need to take more advantage of Unit 5. I'm going to make it, I'm going to switch to Unit 5 of Facebook, and that'll be just where virtual kids talk, just virtual stuff, something that the regular kids wouldn't get, but that would be a virtual conversation. So I'll try and switch that up to Unit 5 of Facebook. Okay, thank you all. Have a good weekend. See you Monday. Bye-bye.